I don't even know if this is gonna work or not. It looks like it. Hopefully, I didn't hurt your ears just then. Okay, so the video I made to set up this the graph doesn't match up with what we are going to be doing. So, oops, I guess I don't like that. 100%. But anyways, in the past, we've graphed this here, but what happened is that what you ended up with, and let's see, where is this Excel sheet? That's a Word document. And so we get our error bars are going to be in the f squared variable because that's what we measure. With the spin, you'll see we're going to be using a stopwatch and measuring periods, and we get a plus minus on the period, and we end up with plus minus on that's nice. So I didn't nuke all of my work from the other day. The point is that we are considering f centripetal, so we're going to measure the we're going to assume a certain radius. We're going to assume that I got to make sure this all is on the screen. Let's go back to the manual. Here we go. That's the pre-lab. Here is the actual lab. Right. So we're going to measure the force centripetal. We're going to assume that it is the mass of this on the hanger, and then we're going to have a spring stretch a certain amount, but we're going to measure it independently. And so we are going to say that the F centripetal is a independent variable. So we're going to pick different F centripetals, and we're going to measure F squared, and we're going to do this by, let's see, the data table. Well, that's not very useful. So, we're going to change the spring constant, basically. We're going to connect different positions, and it's hard to talk about when we don't have the equipment in front of us. But what happens is then the F centripetal is, we're going to assume that the F centripetal is equal to the stretch of that spring at a certain point, and the apparatus is set up so that the object will be, when we set it up, when it's just like the middle diagram here, then the F spring and the F centripetal will be equal. And so when we measure F centripetal, or we measure the period anyway, and we'll see how that works when we're in class. We can assume that we're measuring this period. We're assuming the mass and the capital R are going to be constant, and we're picking the F centripetal by picking different different spring constants, actually, in the way we connect the spring. You'll see when we're in class. So it turns out then that F centripetal is the independent variable, and that goes on the x-axis. The way this lab is set up, we ended up with horizontal error bars, and it's not trivial. Well, these are vertical, but in the original lab, let me find this spreadsheet of mine. In the original lab, you would have ended up with horizontal error bars, and that's just not the right way to go. So what we want to do is we want to have F centripetal on the x-axis, and the frequency squared on the y-axis. because then we'll have, that's where we have our plus minus in the measurements we take in class. All right, so this is, I don't know if this is real data anymore or not. I may have simulated it, but we're going to take the time period for, say, 10 revolutions, and so then in this case, we quoted a rather large plus minus time here, I guess simply because I wanted error bars that would show up. Well, although we've been using 0.75, I think in the past, or 0.5, so it's not that far off. And then we get the period is the amount of time for whatever number of revolutions, and divided that there. In this case, it's 10 every time. And then the error then, plus minus, is simply dividing by 10. Okay, then the frequency is 1 over the period. And then, of course, frequency squared, we just square it. That's easy. But now we need to incorporate, we need a plus minus f. And so I'm going to select those. I'm going to insert. I think that the one I set you guys up, let's see. Yeah, I did that for you. Okay. So let's just use this one. It's already done. I made nice, strong borders there. Okay. So I guess I have, in this one, I'm asking you guys to do it. So let's see, view, zoom to selection. Oh, we can't do that because it's off the screen. Let's get this just right here. Fit it all onto the screen. Let's see if that, well, it's enough to get started. Okay, so this is the easy part. This equals the time for 10 divided by 10, or the number of revolutions. I didn't just type in 10. This way, if I use 5 revolutions and 10 in the next one, I don't have to I just type in how many I used. And the plus minus then is, or sigma, is just equal to the sigma of the total time divided by the number of revolutions again. So now we have our periods for the different f centripetals. And next is the frequency, which is equal to 1 over the period. And now we need the plus minus here. So we have to remember, I'm going to turn on the drawing tablet. We have our table of formulas for the error propagation. Excuse me. So when we have f equals to a times b, or a over b, then the sigma on the f equals the result. And now this f is not the same, it's just the result. And then times the square root of sigma a over a squared plus sigma b over b squared. And the nice thing here is that a equals 1 for this. A equals 1, so sigma a is equal to 0. And so we end up with, and we don't have to use a different letter, is the plus minus capital T divided by T. And I should have left myself a little room there. Let's see if I can cheat it by moving over the equal sign. and we put f here, and we put the square root. Of course, that's pretty straightforward then, taking that square root. So I just say that it's equal to the frequency we ended up with times the plus minus period divided by the period. Pretty straightforward. So now I have that. And the square is pretty easy too, equals the frequency squared. And then there we go. Now, the plus minus, we use yet again, this f equals a times b. And in this case, our f squared is equal to f times f. That's pretty straightforward. So the sigma f squared is going to be equal to f squared times the square root of plus minus f over f squared plus minus f over f squared. And that becomes f squared times the square root of 2, because now this is going to equal 2 times that. And then I take the square root, and I get plus minus f over f. So it's only just slightly more complicated. Equals f squared times sqrt 2 times plus minus f divided by f. Bingo. So now we have an error bar for each of them, each of the f squareds. We're on our way, huh? Okay. So we have a mass, and so something is not, oh yeah. So we are going to use different masses. At least that's what it says here. Let me pause this. Okay, now I remember. So, in fact, this is, we're going to be hanging some masses to help us to measure the force needed to stretch the spring. There is a mass of the bob, this thing that's going to be hanging down, but that is our mass for the spinning motion. There's a pulley thing here, and we're going to put we're going to hang a weight. I can draw on this, huh? We're going to, there's an ability to put another hook on here, and there's a pulley here. And, well, let's put it over here. And then we're going to hang we're going to put masses here, and we're going to change the spring we're going to change the spring constant by, you'll see, we're going to change the amount of the spring constant. So that's going to mean that the force that we need to achieve equilibrium, meaning having this thing hang straight up and down, is going to be different each time. So this mg here in the vertical direction is important for determining the equilibrium condition, but that's the mass of the bob, not the masses that we're going to be measuring. We measure the mass of the bob once, but we're going to be, with each different spring constant, we're going to be measuring a mass. So I suppose I should put this a capital M, and although, yeah, only because we use a little m in the equations, but that little m is the mass of the bob. All right, so this one's fairly straightforward. This is going to equal 9.8 times the various masses that we hang on from the hanger. And now we have that, and there's no plus minus on it. There is, but it's so much smaller than the plus minus on the f squared that it's not worth mentioning. Okay, so now, as always, we need to get a fit parameter table. And I suppose we can, for now, let's just do this. And, oh, wait a minute, I got another idea. I'd like to get these guys out of the way. I suppose since I'm recording this, I could just erase them. Oh no, wait a minute, I don't have to erase it. I can move them like this. So now I can reuse them in the future. Okay, so I just want to put my fit parameters down here just so as to, well, I think I have all the columns I need, but I just want to try to keep this all on the screen for you guys. Okay, let's see what happens. Excuse me. Alright, so we have our slope. We have our y-intercept. And I don't think I need my tablet anymore. I'll turn that off and put it to the side. It was screwing up my typing. We need the sum of the residuals squared. We need the sum of the chi-square. I'm just going to be lazy and not. And we need the sum of the square total, which we'll get back to in a minute. And then we can do our r squared, capital R squared, for a linearity test. Okay. I can make this a little bit bigger. And, well, first of all, let's make a graph so we get a guess. So we have, we want this to be on our, well, this is easier. What it's easier in this case is to first say insert a scatter plot, and then we want to select data. And I might have outsmarted myself, but we'll see. Here we go. F squared. And the x values are, and I can't move this out of the way, can I? So I'm going to have to cancel this and get this out of the way first. Okay, let's try again. Select data. Add, so this is the f squared, and then the x values are the FCPs, and the y values are the f squared. There we go. And so now we've got our data plotted. And it looks like the slope is about 0.3. 0.3, oops. And we'll just call the y-intercept 0. We hope we expect it to be 0, but let's see. Then the rest we don't know yet. So this is, let's see. So we got to redo that. That's a leftover. This equals the slope, and we need f4 times the y value, which is FCP, plus the y-intercept, and f4 again, of course. And now we've got a fit line, we got residuals, so it's already there. Maybe, so you got lucky I didn't clear this for you. And of course the chi-square is just the equals the residual. Oh, well, excuse me. We do need another column. So I insert, shift cells to the right. There we go. We need the res squared. And excuse me, this equals that squared. It's pretty good. It looks like I hit it pretty well for the slope. And the chi-squared is just equal to the residual squared divided by the plus minus here. And we have to square it. Now I'm a little worried, so I'm going to add parentheses just to be safe. Right, and that we know then that the larger error bars will be downplayed. And let's see, we need the for the SS total, we need to get the average. So this equals average of the data points. And we need the data minus the average squared. And that's sort of quasi-variance. So let's see. Data minus the average. And then we need F4 key. And we also ought to put this in parentheses too, because we want to make sure that we're squaring the whole thing. Just to be safe. And now, whoa, auto-sized, huh? And let's make that a number. We'll give it some extra digits. There we go. Yeah, I wonder why this one didn't do it. Well, number. That looks okay. So we can do equals to the sum of the residual squared. And then equals the sum of the chi-squareds. And we have, yes, the sum of these variance squares. Oops. Equals sum of this mess. And our r squared is equal to 1 minus the sum of the residual squared divided by the sum of SS total squared. And bingo. And well, that's pretty respectable already. And let's change this. I think I'll add another decimal place. Sweet. So let's add our, oh yeah, I want to add our fit line, but we can get a little clever because we want to have the line go all the way from 0, and we want it to pass through the last point. We don't want it to just end at each endpoint there. So we want to make this 0. That one's easy. And so the maximum is 4.9, so we'll make this 5. That'll make a nice looking line. And we just have to extend that down. And we should, oh, why is it that I don't get, okay, let's try this. I just getting lazy. I want the format marks. And so now we just, the grid, the grid. Nice, so that's there. Sweet. So let's select data. Want to add. And as we've done over and over again, the fit, the X values are now here. And the Y values are here. And we're almost home. So that looks pretty good. And now, I don't know why oh, that's a straight line. It just doesn't seem like it just yet. So, options, series fit, on a solid line. And I always like my fit lines to be red. And I want to make it thin. And then we want to get rid of the markers. Okay. So there is our pretty fit line. We can add error bars. I'll add those in a minute. So now we can finalize our fit by using the solver. We want to minimize, and let's see, there's our chi-square. And by changing our slope and our y-intercept, and make sure to uncheck that one. And it looks like we have a winner. Nice. And so we need to add error bars and we need to add labels. You guys ought to know how to do that by now. Unfortunately, I don't remember. Well, the sum of the chi-square went down. It was like 4, right? Yeah, this used to be 919. Now it's 992. So we're on our way here. That's it. We're in pretty good shape as far as the linearity. Anyway, that's important. We always want to check that. And I don't know what's going on here, but this thing is making in mine anyway, it's making all the lines gray instead of black. I just decided to make it bigger, heavier duty, and there we go. And of course, you have to make statements about the slope and all that, because the slope now is 1 over, but we know the mass now with the bob. Oh, here's what I did, m bob, and we know what r is. We pick r, you'll see, but that's so we can interpret the slope. But for now, we just want to get this going on. And don't forget now that we can use the sum of the chi-squares to get our plus minus slope, but that's another video. All right, so now I just got to get this up onto YouTube, and I'll send out an announcement that it's waiting for you. See you soon.